Hello, Arshita. Good afternoon. Good afternoon. So we will wait till some more students join. Okay. Good afternoon. Good afternoon, everyone. Good afternoon. So, good afternoon. I think we can start. So let me review what I was talking about. All right. So we were discussing the precession of the equinox, and I mentioned that because of the tidal torque, largely due to the moon, the axis of the Earth's spin, it spins about a direction that is perpendicular to the plane of the Sun Earth orbit. Now, this is analogous to the top precession. As you know, when we were kids, we used to play with tops. And when the rate at which the top was spinning slowed down, it would wobble and precess. The reason was that the gravitational torque due to Earth will start becoming dominant compared to the angular momentum of the top. And that is the reason when it got a little bit tilted, then the top will start precessing. This physics is more or less what is involved in the precession of equinox concerning our planet Earth. Right. Now, let us go further to the planetary motion. And as I mentioned, that Tycho Brahe's accurate observations led Kepler. Kepler had joined the observatory of Tycho Brahe, and Kepler looked at the data and he found a pattern in the data. By now, we all know the principle behind the scientific method. So, a scientific method involves first experimentation and data collection, and then finding some pattern in the data or finding some cause and effect relation in the data, and then build a model to explain the relation between different concepts that the data or experimental results are pointing at. But then comes the crucial thing. The model must predict something which was earlier not experimented on. So the model predicts a new effect. And if the new effect is observed and experiment later, then the model is good. But if the new experiment actually goes against the model, then the model has to be changed, modified, in order to take into account the result of the new experiment. And that's how the scientific model building goes on. Kepler's law illustrates this scientific principle very nicely. Tycho Brahe's collection of data in his observatory was analyzed by Kepler, and Kepler found that the motions of solar system planets can be fit into ellipses. So, in particular, Kepler found that if Sun is taken to be located at one of the foci of an ellipse, then the motion of the planet forms the locus of points of an ellipse with Sun as the focus. But that's not all. So, first law of Kepler stated that all planets move in ellipses with Sun in its focus. The second law was based on position and time measurement. So Kepler looked at the position of the planets at different instants of time, and he found a pattern in the position and time measurement, and the pattern was this. For every planet, Kepler found that first law, of course, stated that the planet moves in an ellipse. The second law states, which was essentially what Kepler found, that in equal intervals of time, the ray from Sun to the planet traces out equal amount of area. That means what? That when, let's say, the planet is here, and in some time interval t, planet comes to this position, so the ray from the Sun to the planet has swept an area which is shown here in a very light shade of violet. And if you take the planet at a different position, and in the same time interval, it goes from this point to other point, the segment traveled is of course less compared to the segment traveled in the previous case, but the area swept out by the ray from the Sun to this position is equal to the former case. And Kepler therefore stated that in equal time interval, the area swept out by a ray from the focus to the planet is equal in equal intervals of time. Then comes the third law of Kepler. Third law of Kepler is actually what is the dynamical aspect of planetary motion. Third law stated that take any two planets. Okay, so let P1 be the time period over which a full orbital motion is executed by planet 1, and P2 is similarly the time period over planet number 2 goes around the Sun covering 360 degrees of rotation. Then Kepler found that for any two planets, planet P1, P2, being the orbital period, P1 by P2 whole square is equal to the cube of the ratio of the distance, the semi-major axis of the ellipse corresponding to planet 1 and planet 2. That means Kepler established a proportionality law which stated that the orbital period of a planet is such that the square of the orbital period is proportional to the cube of the semi-major axis of the ellipse on which the planet moves. Now, imagine that today we might think that Kepler's law is quite simple. After all, we learn it in school as well as BSc days. But imagine the excitement among astronomers during Kepler's time. Here is a man who is talking about ellipses which are essentially geometrical entities which one studies uh, based on what is discovered on Earth, and the same geometrical entities seem to be describing motions of cosmic objects. Now, that must have been a very profound result for those days. And it was for the first time geometrical entities were being used in laws of motion concerning cosmic objects. Obviously, it was a, an excitement time for astronomers, and we must pause and take a note of a matter of significance. What is that? The first quantitative law of dynamical motion came from astronomy. Of course, astronomy has been one of the oldest sciences, but Kepler's law also tells us that first mathematical law governing position and time actually was associated with cosmic objects, and they were the first to be discovered. Now enters the next physicist who was to revolutionize the entire field of physics and the cosmos, and that is Isaac Newton. But before I talk about Isaac Newton, I must state that he indeed stood on the shoulders of giants to discover new aspects in physics. In fact, he himself mentioned that. And who were these giants he had in mind? Kepler, of course, as well as Galileo. Galileo is truly said to be the father of physics because it was Galileo who established, by making systematic and controlled experiments concerning time intervals and displacement and inertia, and he established that uh, the accelerated motions do not depend upon frames of references that moved uniformly with respect to each other. And certainly, the quantitative measurement with great accuracy he performed using very good uh, clocks and distance scales showed that if one wants to learn about the fundamental nature around us, then the way to go about is to do very fine controlled experiments using quantitative language. That means using mathematics. In fact, Galileo in his writings does point out to the importance of mathematical language being the language of the physical world. Right, now let's come to Newton. Newton, it is said, again, whether it is true or not cannot be vouched for, but it was the French philosopher Voltaire who was exiled from France because of his satirical writings. And after the exile, Voltaire sort of spent considerable amount of time in England, and obviously Newton being quite a famous person by that time, Voltaire visited Newton's place. Unfortunately, Newton was not present, but Voltaire met Newton's niece, and the niece informed Voltaire that some time back Newton was resting under an apple and he saw an apple and he was struck by an idea, and therefore he is working out his ideas in a very thorough manner. And Voltaire popularized this story of apple falling on Newton's head, and that's how Newton discovered gravity. Uh, well, that's the folklore, and we don't know whether that's how Newton discovered the laws of gravity. However, how did Newton figure out that if you take 2 point masses, so imagine that you have mass 1 and mass 2, then Newton said that the force between the two masses, they are proportional to the product mass 1, mass 2, but inversely proportional to the square of the distance. So here is the quantitative expression. So in other words, if you have a mass small m and mass capital M separated by a distance r, then the force between them is attractive and is given, the magnitude is given by a constant, which today we call Newton's gravitational constant, times the product of the masses divided by square of the distance between them. How did Newton figure out that this must be the case? After all, he had not done any experiment concerning forces between two objects. And that is where lay the genius of Newton. Newton knew that near the surface of the earth, when you drop an object, the object falls with an acceleration 9.8 meter per second square if we adopt the SI units. All right. So this is something which we constantly experiment upon from school days. So if you drop an object, the object will fall with an acceleration. Every second, it would the velocity will increase by 9.8 meter per second. All right. Newton realized, and that is where the genius of Newton lay. Newton realized that moons going around Earth is nothing but moon falling under the gravity of Earth. Right? So this is something which called for a leap of imagination. Yes, when we drop objects fall towards Earth, no doubt. But the fact that Moon is going around Earth is actually Moon falling due to Earth's gravity is something which struck only Newton at that point of time. The next point is Newton, by then he had already written down his laws of motion, and he knew that if an object is going around in a circle with a speed v and distance r, the acceleration is nothing but v square by r, the so called centripetal acceleration. And Newton knew the velocity of moon around Earth as well as the distance from Earth to the moon. I will talk about this distance measurement soon, but how did Newton figure out the speed of moon? So imagine the moon is going around the Earth. How do I find out the speed of the moon? We know that moon goes around the Earth in roughly in a circular orbit, and the period of this orbital motion is about 28 days. And therefore, if the distance from the center of Earth to the center of moon is known, then the circular orbit distance is simply twice pi times the Earth moon distance, the so called 2 pi r circumference of a circle of radius r. So in roughly 28 days, moon covers a distance of 2 pi r, where r is the distance between the Earth and the moon. And therefore 2 pi r by 28 days gives us the speed. And hence the centripetal acceleration can be determined by the formula v square by r. And then when Newton compared this acceleration of the moon around Earth to the acceleration of any object near the surface of the Earth falling, he found, and this can be done as a simple exercise. I urge all of you to do this exercise. All right. Uh, I must ask you to pause for a while. I think I have a visitor to my house. One moment. Just one moment. Yes. So because the v square by r expression gives the acceleration, and the acceleration of the moon is at a distance of r moon from the center of the Earth, while any object near the surface of the Earth that falls with an acceleration 9.8 meter per second square is happening at a distance which is the radius of the Earth re. Newton immediately established that the two accelerations are proportional to 1 over distance square. So in other words, 9.8 meter per second square divided by the acceleration of the moon, okay, turned out to be equal to the square of the distance of the moon from Earth divided by the square of the radius of the Earth. And that is how Newton established the inverse square law of the gravitational forces. But note that in this analysis, we have made use of two length scales. One is the radius of the Earth, RE, and the other is the distance from the center of the Earth to Moon, Rm. So you might wonder, how did the astronomers or the geologists or physicists at that time determine the two distances? Okay, let's come to estimation of distances in astronomy. Suppose you wish to estimate the distance of moon from Earth. By the way, in this picture, uh, there's a small problem. I have put this bright point labeled as S as Alpha Centauri star, but actually one cannot use the method that I'm going to outline now to measure the distance of the star using Earth as the baseline. While this method from Earth can be used to measure the distance of Moon. So this is how one would measure the distance of Moon from Earth. What one does is that uh, suppose we know the diameter of the Earth. I will tell you also how the diameter of the Earth was measured for the first time. But suppose we know the diameter of the Earth and we wish to find out what is the distance of Moon from the center of the Earth. So what can be done is the following, that you call your friend who is at a place, let's say he is in New York. So this point is, let's say, New York. And consider another city which is diametrically opposite to New York. Okay, so if this point is New York, let's say, then you go to a diametrically opposite point. It'll be somewhere in China, probably. And you call up your friend and you decide that in the evening when moon is at the zenith, you both of you decide when the moon is at the zenith according to you, not zenith. Let's say moon is just about rising. Zenith will be here somewhere. So moon will be rising, while the opposite, diametrically opposite person, you also ask the person to point the telescope at moon when it is rising. Then obviously, with respect to the local vertical, the direction at which the telescope is pointed, when the telescope is looking at the object, here it is moon, the angle you can measure with respect to the baseline, namely this diameter, you can measure the angle, the line from this point to the moon and the line from point B to the moon. You can measure the base angle. If you know the base angle, the third angle of the triangle can be established. Remember, the diameter and the two rays, they form a triangle, and we all know from our school Euclidean geometry knowledge that sum of the interior angles of a triangle is 180 degrees. So by measuring the direction towards which the telescopes at the 2 points point, one can measure the base angles and thereby infer the third angle. And then the distance from the center of the Earth to the moon can be easily established using the Euclidean geometry. And for objects that are very far away, simple result would be that if this angle is known and the diameter of the earth is known, the diameter by the distance of moon from the earth is the angle given in terms of radians. So once the third angle has been measured in radians, then all one has to do to find out the distance of the moon from the center of the earth is to use the relation, the diameter divided by the distance of the moon from the center of the earth is simply the third angle in radian. For distant stars, can't use the diameter as the baseline because this angle will be so tiny that it will be submerged under the errors of angular measurement. And that is the reason why one has to go to a bigger baseline. By the way, this method is called the parallax method of measuring distances in astronomy. So if one wants to estimate the distance far away, stars which are far away located, then one has to use the orbital motion of Earth around Sun. And once the Earth-Sun distance is measured, then the diameter of the Earth's orbit can be used as the baseline, and again using the parallax method, whereby one measures the base angles by looking at the telescope's orientation while the telescope is focused on the distant star, one can measure the parallax angle rho, and from that one can find out the distance of the star from the sun. This parallax method of measuring distances is what is used in measuring close by stars. If you want to measure distances of even further objects, then parallax method will not work, because once the object becomes extremely distant, you can see that this parallax angle rho will become tiny. And we all know that every measurement is associated with errors. And once the parallax angle is comparable or becomes smaller than the errors involved in measurement of angles, then this method will not work. For very distant objects, there is another method which is used, and it is essentially the luminosity and distance relation. Okay, so here I have to define certain things. First thing is, what is a luminosity? All right. So suppose you have a radiating object, and let's say we have considered the radiating source to be such that the radiation is isotropic. That means it is emitting equal amount of radiation in a tiny solid angle uniformly in every direction. All right. Then luminosity is defined as the energy of radiation radiated per unit time. Right. So if you consider a light bulb of 1000 watt power, what this means is that a 1000-watt power light bulb radiates 1000 joules of energy per second. So 1000 watt is essentially the luminosity of a 1000-watt bulb, while our nearest star, namely Sun, its luminosity is about 4 multiplied by 10 to the power 33 ergs per second. It is a humongous number. So let me repeat again. The luminosity of Sun is 4 into 10 to the power 33. That means 4 followed by 33 zeros ergs per second. Later on, we will also learn what physical processes cause emission of such large amount of energy from stars. All right. So after having defined luminosity, we come to the notion of flux. So if luminosity is represented by L and flux by F, then flux is defined to be amount of energy received from a radiating object per unit time, per unit time, per unit area. So once again, let me repeat. Flux is the amount of energy received or detected per unit area of the detector per unit time. All right. If that is the case, then if you have a uniform source of luminosity, that means a source that is steadily pouring out energy at a constant rate in an isotropic fashion, then at a distance d, if your detector is located at a distance d, then flux detected by the detector will obviously be luminosity L divided by 4 pi d square. Why is that so? Because Euclidean geometry tells me the radiation which is being radiated in an isotropic fashion, it will be distributed isotropically over a surface area of 4 pi d square when the radiation moves a distance d. After all, we know that a spherical surface of radius d has a surface area 4 pi d square, and hence for an isotropic uniform luminosity source, there is a definite relation between flux, luminosity, and distance. Flux is equal to luminosity divided by 4 pi times square of the distance. I see that there is a question. Yeah, so the question is, can luminosity of a star and the intensity of light radiated by that star be used interchangeably? The answer is no. Intensity is defined in a different manner. So, again, let me define the luminosity once again. So luminosity is nothing but amount of energy radiated by a source per unit time. So its physical dimension always is energy per unit time. Intensity, on the other hand, so there are several notions of intensity. If you are talking about specific intensity, then specific intensity is defined as energy crossing per unit area, per unit time, per unit solid angle. So the specific intensity has a physical dimension of energy per steradian per second per area. So obviously, luminosity and intensity are two different quantities. All right. Okay. Now I have limited amount of time. I have about 18 minutes. So I will be able to cover one very surprising phenomena, which was which we all see, but we never sort of wonder about it. All right. But great physicists and astronomers observed this very standard phenomena and wondered about it. Okay. This phenomena is called Olber's paradox, or why is the night sky dark? Okay. All right. So we all know that at night the sky appears dark. Okay, first of all, let's go back and ask the question, why during the daytime the sky doesn't appear dark? The reason we all know, it is due to atmosphere's scattering the solar light. If there was no atmosphere, even in the daytime, we would find the sky to be dark with glittering stars. And in the direction of the sun, of course, we will see a very bright sun. But otherwise, the sky will be dark, there'll be stars, there'll be sun, there'll be moon. What happens in the daytime, the reason why the sky doesn't appear dark is our Earth has an atmosphere, and the radiation from the sun, when it is reaching the Earth, the intervening atmosphere, the gaseous atoms and molecules present in the atmosphere, they scatter the solar radiation, and the scattered radiation is in random direction, and that is the reason why the day sky appears bright. And in fact, it is also related to the question that why is it when sun is close to the horizon, sun appears uh, reddish, but when sun is at the zenith, sun appears yellowish white. It is again the phenomena of scattering, because we know Raleigh's scattering law tells us that shorter wavelength light gets scattered more than longer wavelength light. What happens is when the sun is at the horizon, then it the amount of you can easily draw a picture and show that the amount of uh, distance traveled by the radiation through the atmosphere is longer, and that is the reason why the blue part of the light getting scattered more, while the red part suffering less scattering. So because when the sun is in near the horizon, the radiation is crossing a large column density of Earth's atmosphere, and thereby the blue part of the radiation gets essentially attenuated compared to the red, and therefore the sun appears red. While when the sun is at the zenith, the column density of the Earth's atmosphere is not as large. All right. So we know that during the daytime, the sky being bright is because of Earth's atmosphere. If you go to moon, if you look at, if you are standing on moon doesn't have much of an atmosphere. Whether it is day or night, doesn't matter. The sky will always appear dark from moon. Right, now let's go back to the original question. We all know, every one of us observe that at night the sky is dark. We never question, right? We say, oh, sun is on the other side, and therefore, why shouldn't the night sky be dark? But it is said that the Kepler probably thought of this question for the first time. There are many people who independently thought about the problem of night sky being dark. So perhaps Kepler was the first one. There were people like Deschutes, Laplace, and finally Olber, and that's how this paradox is referred to as Olber's paradox. But this paradoxical question was posed as early as Kepler. And what really is the problem about night sky being observed to be dark? Kepler, let's say he was the person who for the first time raised the question. Kepler asked the following question, that universe seems to be infinite and stars are there everywhere, right? And universe seems to be existing from time immemorial. All right. So note the assumption that Kepler is making. Kepler is making the following three assumptions. First assumption is universe is infinite in extent as far as space is concerned, and everywhere there are stars, and there's no reason not to believe it. After all, Copernican principle is involved. We are not the center of the universe, but at every other point also universe must look the same. And therefore, if universe is indeed infinite in extent, then there should be stars everywhere. And if there are, if the universe is infinite extent, there should be infinite number of stars. And we assume that universe has been existing from time immemorial. That means age of the universe is infinite. And therefore, take any star anywhere, light from the star must have reached us today, because the universe has been existing for time immemorial, and if the stars were also there since then, and there's no reason why that should not be the case. So star, no matter where the star is, the radiation from the star must have reached us. Okay. Then Kepler asked the following question, that therefore, if you look at the number of stars in a shell, so imagine you consider a shell close by, count the number of stars, then take another shell, count the number of stars, and the number of stars in shells of equal thickness will be proportional if the shell thickness is very small compared to the radius of the spherical shell, then number of stars would be proportional to the volume of the shell. Okay, because number density of the stars will be more or less uniform. Leave aside statistical fluctuation, but given the Copernican principle that we are not the center of the universe, if you are at any point in the universe, the universe must appear the same. If this principle is correct, then number density of stars must be uniform, and hence number of stars in a given shell would be proportional to the volume of the shell. But what is the volume of the shell? Volume of the shell, if the shell thickness is very tiny, then volume is surface area of the shell multiplied by the thickness, as simple as that. Take the surface area of the shell, which is 4 pi r square. If you take a spherical surface of radius r, then surface area is 4 pi r square. And if the shell thickness is, let's call delta r, if delta r is tiny compared to the radius r, then the volume of the shell is surface area times thickness of the shell. And therefore, the number of stars in a shell of radius r and thickness delta r is proportional to 4 pi r square into delta r. Then you ask, what is the total amount of radiation being received from the shell? The luminosity, if it is L for the stars, the flux is proportional to L divided by 4 pi r square. So flux, total flux at Earth due to all the stars in the shell will be L divided by 4 pi r square times 4 pi r square delta r, which is the volume, times number density. But then r square cancels out and you're left with simply luminosity times delta r, and delta r has to be summed up from u to infinity. And therefore, this argument tells us that the flux measured must be infinite. And therefore, the night sky ought not to be dark, it should be infinitely bright. There's another way of looking at the same problem, more visual, not mathematical. So imagine there are stars are uniformly distributed, and you're here and you're looking at stars at different points. Then you are only seeing the stars to be projected on the sky plane. So when you are here, from this area, 2 stars will be projected on the sky from a radius of r. From radius of 2r, 4 stars, because these 2 stars will be there. And as you go further and further away, more and more stars will be projected. And therefore, if you look at if r goes to infinity, all the stars should be projected. And therefore, the night sky should be at least as bright as the surface of the star. Okay? Have I made myself clear? So please think about it. And maybe later on, if there are questions, you can ask me. What Kepler, Lescheteux, and Laplace, Olbers, all these people, they realize that there is some problem. That indeed, if the universe is infinite in extent, and if it is infinitely old, so that no matter how far the star is, the radiation from the star would have reached us, then if this argument is correct, then the night sky should not be dark. It should be at least as bright as the surface of the star from this argument. Okay? But the fact is that night sky is dark. So one of the assumption must be wrong. Okay? Which assumption is wrong? Is the universe being infinite in extent? Is it wrong? Or is it that universe being infinitely old, that is wrong? Or is there something else? It turns out that if you relax one of the assumptions, so suppose you say universe is not infinitely old. Rather, let's say universe was born 13.8 billion light years before. Well, not light years, 13.8 billion years ago. Light years is a unit of length scale. So I made a mistake. So imagine that universe is only 13.8 billion years old. Can we resolve the Olbers paradox? The answer is yes. So let's resolve it. So imagine the universe is 13.8 billion years old and the universe is infinite in extent in space. If that is the case, then today we can only observe up to 13.8 billion light years because radiation from a star travels at a finite speed. We know that speed of light is finite, and therefore if this circular line represents a circle or a spherical surface having a radius of 13.8 billion light years, then a star beyond this spherical surface cannot be seen today. Why is it so? Because in order it to be seen, light must have reached from that star to us, but the light will take more than 13.8 billion years to reach from that star. But that can't be the case because universe is only 13 point, universe was created only 13.8 uh, billion years ago, and stars did not exist as far as before the universe was created. So today we can observe only up to a distance of 13.8 billion years. Of course, as universe becomes older and older, this observable surface will keep on increasing in its area. And we'll see more and more parts of the universe. But today, the number of stars we can see today are all within the sphere of radius 13.8 light years. Why? Because universe is 13.8 billion years old and the scale 13.8 the scale light year means the distance traveled by light in 1 year, and therefore if the universe was created 13.8 8 billion years ago, the maximum light the maximum distance a light could have covered since the origin of the universe and today is 13.8 billion light years. So our observable universe is limited to a sphere of radius 13.8 light years, billion light years. Now, if you calculate the flux due to all the stars within this sphere of radius 13.8 billion light years, you will see that the flux is very tiny. And no wonder that the universe is no wonder that the sky is dark at night. By the way, you could have also solved the problem by saying that the universe is not infinite in extent, but it has a finite extent. But in the Euclidean geometry, if you take a universe having a finite extent, meaning universe is only there up to this, within this region, beyond it there is nothing else, that means there is an edge to the universe. So that means stars are there only within this volume. After that, it's all vacuum. That makes it very unnatural. It violates the Copernican principle that universe should look the same from every spatial point. All right. You might ask, uh, what about steady state model? In steady state model, which was championed independently by Fred Hoyle, Thomas Gold, all right, they had assumed that the universe is not only infinite extent, universe is also existing for infinite amount of time. So you might immediately raise the question, wouldn't in steady state model universe the sky, night sky must be bright? The answer is no, because in steady state model the universe is also expanding. So objects are moving away from each other, and therefore, and Hubble's law, which we will discuss soon, tells us that further away an object is, the redshifting is larger. So in steady state model, again, Olbers paradox is averted by using the redshifting, because from distant radiating source, the light gets dimmed because of the redshift. Effectively, only objects within the observable universe contribute to the flux at any given point of time. All right. So, I have just realized that we have crossed the time. So, I will stop here. And if there are questions, I'll take the questions. Yeah. Uh, are there any questions? All right. Uh, uh, there's a question from Priyamvada Kameshwar. Yes. So when moon um, appears at the horizon, indeed, its color is not whitish; it is yellowish. And remember, moon uh, radiates because of scattering of the light. It doesn't have much of the higher frequency radiation, and that's the reason. And also, it doesn't have much of the longer wavelength too. So, if you look at moon rising at the horizon, it appears yellowish, and in a clear night sky, when moon is at the zenith, it appears whitish. But before I go to other questions, let me also give you an exercise. We all know when sun or the moon is rising on the horizon, they appear bigger than when they are in the mid sky. When you see moon at the zenith, it appears much smaller, while when the moon is rising, it appears very large. And same is true about sun. So please find out why this is. So this uh, can be one of the questions you can think about. You can try to find out sources from where you can find the answer. Uh, there's another question from Dinesh Singh. It says, according to you, sir, what is nature of universe? Well, not according to me. Remember that in science, we form the idea of the physical world from first experimental observations and then building mathematical models. By now, what has been established is that the universe is expanding. And when I talk about Hubble law, we will discuss it more. So, universe is made out of stars that are conglomerated in the form of galaxies. We'll talk about all these as we go through the course. We'll talk about all that. So, the basic building blocks which radiate energy are stars, but the stars are not isolated. They come in large groups called galaxies. And so, galaxies are basically the units or the building blocks of the universe as far as matter is concerned. But note, the space time of the universe is also dynamical. Okay. And that comes from general relativity. So, universe brings about an interplay of physical laws of matter as well as space time. And so far, what we have discovered is that we live in an expanding universe, and not only that, the rate at which universe expanding is actually increasing with time, so which is called the late time accelerating universe, and so on. Right. So there is another question from Ankita Shelley. It says, why do mean moon appear red sometimes? Again, this is the same phenomena as scattering. So if the radiation of moon is crossing a very dense matter, so sometimes what happens is that you could have dusty atmosphere, and the dust cause a lot of scattering. But longer wavelength, as I was mentioning, the Rayleigh scattering law states that longer wavelength suffer less scattering. So, very often, when you have a dusty atmosphere, then whether it is moon or the sun, when the radiation crosses the dustiest atmosphere, they appear red. Right. Priyamvada has another question, which states any animal who is able to see a broader section of the EM spectrum beyond optical will perhaps see a brighter night sky. Yeah, it will see a brighter night sky. It will be able to see many other radiation, the so called X ray background, gamma ray background, infrared background. But yet, all this background radiation is much, much, much less compared to the daytime intensity of the sky. Okay, there is a question from Shubham Gangwar. Why Mercury is in spherical form? Well, uh, uh, by now we know big uh, objects bigger than asteroid size object mass wise, the self gravity is so strong that it crushes it, sort of overpower the self gravity of the object, overpower the electromagnetic van der Waals forces that maintain the shape of a solid, and therefore they uh, attain a spherical form coming from the hydrostatic equilibrium. We will talk about this maybe in our uh, after 2 or 3 weeks. We'll talk about the hydrostatic equilibrium that makes heavier objects in spherical shape. And Mercury is also uh, heavier than asteroid. It's much heavier than Moon. Moon itself is spherical, uh, and there is, although Mercury is close to the Sun, but it's not so close that the tidal force of Sun would deform it. Okay, tidal force is proportional to 1 over cube of the distance, and therefore it falls off faster as it is 1 over cube of the distance. Okay, so the tidal force on Mercury is not so severe as to make Mercury uh, tidally deformed. Ankit Yadav, can you spell out your question? You have written MEG gradient pressure. I don't understand what you mean by that. Can you spell out in details what you mean? Probably Ankit means what I just stated, that the tidal force which appears due to the gradient in gravity, the tidal force due to Sun is not appreciable at Mercury's. Okay, okay. Right. So this is what I mentioned that, right, Ankit. Uh, as I mentioned, that the tidal force due to Sun on Mercury is not appreciable because tidal force, by the way, tidal acceleration is proportional to the size of the test object and inversely proportional to the cube of the distance of the test object from the main source of gravity. So, two things uh, are making the tidal force less for Mercury. First of all, Mercury size of Mercury is small, and therefore tidal force is proportional to the size of the object. And Sun being at a considerable distance from Mercury, 1 over r cube also makes the tidal force less. Are there any more questions? By the way, I need some feedback. I mean, how many students are uh, uh, okay, let me put the question in the following way. Are there students who are not comfortable with the simple quantitative uh, estimate, the mathematical estimates I have made? They are very simple, but are there students who are not comfortable with these quantitative reasoning that I am adopting in my lecture? because I have to figure out at uh, what mathematical level I should lecture. So I should not go beyond a particular level of using mathematics. Yeah, so please send me emails. Uh, please feel free to send me emails to give feedback on the mathematical level that I must adopt in my lecture. And as I had mentioned, there are many introductory book on astronomy. I personally like the book by Frank Shu titled The Physical Universe. I urge all of you to read this book from the first chapter onwards. All right. If there are no more questions, thank you everyone for being patient. We will meet again on Saturday at 10 o'clock. Okay? Great. So uh, take care. Goodbye. All right. So good. That will stop the streaming of this lecture. Goodbye, everyone. Take care.